Hello and welcome to 3-6 Examples for You. Remember that 3-6 is all about graphing, which is finding all the increasing, decreasing, relative extrema, intervals where you're concave up, concave down, points of inflection, and then graphing it on a special little graph like what we have here. Lots of fun, lots of sentences. Here we go. Alrighty, so we've got y equals x to the fourth plus 2x to the third minus 1. Now we could find the y-intercept here quite easily, and that might be a point that might be nice for us to find. So the y-intercept is going to be at 0, -1. The x-intercept, because this doesn't factor, we're going to go ahead and use calculus to help us find those relative extrema where we're increasing, decreasing, so that we can come up with a nice pretty graph of this. So first off, we'll find the first derivative. Okay, the first derivative is going to be 4x to the third plus 6x squared. I want to find my critical points, so I'm going to go ahead and set this equal to 0, showing that I know how to find a critical point. As I do that, I'm going to go ahead and factor out what they have in common. So 2x squared, that'll give me 2x plus 3. So I have two critical points. I have critical points at x equals 0 and -3 halves. I'm going to draw my little chart over here, I think. This is the first derivative, so I've got 0 and -3 halves. Remember, you got to put them in order, or your little number line isn't going to help you very much. Okay, when I check out how it alters, you're picking points on the left side of -3 halves, putting it into the derivative and seeing what it is. Is it positive? Is it negative? You're picking a point in between -3 halves into your derivative to see if it's positive or negative, and on the other side of 1. Well, you know, because of the way your factors are, this is even, this is an odd power. It's not going to alternate on both sides of the 0, so whatever it is on the right side of 0, it's going to be the same on the left side of 0. It will alternate with the 3 halves, the -3 halves though. So if I just plug in a 1, that'll give me a positive value. Remember, it doesn't alternate on the 0, and that's because of the power on your factor. It's a 2. This is a 1, so that's why it will alternate on it. Okay, so that's going to be a minus. So I already know that I'm decreasing from -infinity to -infinity to -3 halves, and then I'm increasing after that. So I know that if I'm decreasing, then I'm increasing. So decreasing, then I'm increasing. I know that -3 halves is a relative minimum. Remember, you have to write out your sentences. So here we go. My y prime is less than 0 from -infinity to -3 halves. So f of x, or y in this case, y is decreasing from -infinity to -3 halves. Putting it all together means writing everything out. So my first derivative is positive from -3 halves all the way to positive infinity. I can say this interval all in one since 0 is a point on my graph. So y is increasing from -3 halves to positive infinity. Since y changes from decreasing to increasing at x equals -3 halves. And I'm going to put the point here because I need to find the y value. So -3 halves, comma, whatever that y value is going to be, is a relative min. Now to find this y value, you're going to plug it into the original. So you're going to take -3 halves to the fourth power plus 2 times negative 3 halves to the third power minus 1. That's going to give you negative 43 over 16. And yes, you can use your calculator on that. So that's a point on my graph that I can actually plot. Okay. So now we need to find our second derivative so we can find out about concavity. So my second derivative, when I look at that, the second derivative is going to be 12x squared plus 12x. I need to set that equal to 0. I can go ahead and factor out some things all at the same time. That way I'm kind of saving a little bit of space here. So I have possible points of inflection at 0 and negative 1. So if I do my little sign chart, this is the second derivative. I've got negative 1, 0. Now because of my powers, remember, this is an odd power, this is an odd power, so it will alternate. So I really only need to pick a point in one interval. So if I pick a point over here, that turns out to be positive. So this is going to be negative, this is positive. So where I'm positive, that's where I'm concave up. Where I'm negative is where I am concave down. So we get to write our sentences. So our second derivative is greater than 0 from negative infinity to negative 1 and from 0 to positive infinity. So y is concave up on those same intervals from negative infinity to negative 1 and 0 to positive infinity. Okay, my second derivative is less than 0 from negative 1 to 0, so y is concave down on that same interval. Now y does change concavity. Y changes concavity. Changes concavity at x equals negative 1 and 0. So now we're going to write these in the form of a point. Negative 1, if you plug negative 1 up into the original equation, you get negative 2. And then 0, negative 1 are POI. So once again, the only time you return to the original equation is to find the y coordinate. So to find this y coordinate, find this y coordinate, find this y coordinate, we went back to the original and plugged those x values in. Okay, so now when we're ready to graph that, what color haven't we used? Blue. We're going to graph those points. So we have negative 3 halves, negative 43 sixteenths. So negative 1.5, almost at 3, but not quite. We're going to put our little dot there. We have a point of inflection at negative 1, negative 2, and at negative 1, or at 0, negative 1. So we have all these nice little points. Now we need to make sure that we are extra emphasizing the increasing, decreasing, the concavity. So if you'll notice, we are concave up from negative infinity all the way to negative 1 and then from 0 to positive infinity. So we are going to show our concave up. I'm going to start over again. I'm going to go this way. So we are concave up here. Then we are concave down in between negative 1 and 0. So we want to really make sure that we overemphasize that, and then we're concave up. Now we're not quite sure where the x-intercepts are. We're just doing the best we can. We could plug values in and see how close we are if we have the use of a calculator. But what I want us to focus on are the actual points that we do know we can find, making sure that we can see we're decreasing, then we're increasing. Notice we're increasing from negative 3 halves all the way to positive infinity, so make sure you are increasing. Don't drag it down and do a oopsie like that, because then you're not increasing in that section. But we want to make sure that we're showing we're concave up, concave down, then concave up. Okay, let's look at our last example for you. Oh, and it's a trig function. How exciting. Now, the way they have it written, we would probably rewrite that. And let me do that in black so that we're using as many colors as we possibly can. So I would multiply that out, 2x minus 4 plus cotangent of x. Notice we're only going from 0 to pi, so our little graph here is not making quite as much sense as it should have. So if I go ahead and get rid of that, see if I can get rid of that. Okay, so it's cramping our style, we don't need it. Okay, so here we go. We're going to find our first derivative. So the first derivative is going to be 2 minus cosecant squared x. I'm going to find my critical points. So I'm going to set that equal to 0. So 2 minus cosecant squared. I'm going to take my cosecant squared to the other side here. When I square root both sides, I'm going to get cosecant of x equals plus minus square root of 2. If you're not good at cosecant, you can change that into 1 over sine. So if you take the reciprocal of the left side, take the reciprocal of the right side, you're going to get sine is equal to 1 over square root of 2 and negative 1 over square root of 2. Either way, you're going to come up with the same critical points. It's going to occur at pi over 2. Sorry, pi over 4, and 3 pi over 4. Now, cosecant is equal to negative square root of 2 in the third quadrant and the fourth quadrant, but remember your interval here is only from 0 to pi, so I don't need to consider any of the other critical points. I always want to write down that I am looking at my first derivative. I also always want to put those endpoints down so I don't accidentally take my interval too far out. I've got pi over 4, and I have 3 pi over 4. When I plug in values to see what my first derivative is doing, it is negative, then positive, then negative. Okay, now I get to write out my nice pretty sentences. I may do that here in just a minute or two. So I'm going to go ahead and find my second derivative while I'm on a roll. So my second derivative, when I find my second derivative, that's going to be negative 2 cosecant of x times negative cosecant cotangent. It was a chain rule, okay, the derivative of 2 was 0. So I took the 2 down in front, subtracted 1 from the exponent, that's how I got the first part, and then times the derivative of what was inside, the derivative of cosecant. When I do this, it's already kind of all spilt out, but you can multiply that together. So that will be 2 cosecant squared x cotangent x. When I set that equal to 0, I'm looking at where 2 cosecant squared x equals 0 and where cotangent of x equals 0. If I simplified this one, this 2 cosecant squared equals 0, I would divide by 2, square root both sides. I'm looking at where cosecant of x is equal to 0. That never happens. Cotangent is equal to 0 smack dab in between its asymptotes, which would be pi over 2. So when I'm looking at my little chart, once again, I can't go past 0 or pi. I'm at pi over 2. Now this is my second derivative. I always want to mark that so that when I'm writing out my sentences, I know if I'm talking about increasing, decreasing, or concavity. So my second derivative, if I put in a value in between 0 and pi, that's going to be positive. In here it's going to be negative. So now I'm ready to write out the sentences. Yeehaw! Here we go. I know you get tired of writing the sentences. I do too. My derivative is less than 0 from 0 to pi over 4 and 3 pi over 4 to pi. So f is decreasing on those same intervals. My derivative is greater than 0 from pi over 4. Oopsie, got excited there. Close that up. Pi over 4 to 3 pi over 4. So f is increasing from pi over 4 to 3 pi over 4. Since f changes from decreasing to increasing at x equals pi over 4. Okay, and I'm going to go ahead and write out my point. Pi over 4, it's a decimal, or you can leave it as the pi over 2 minus 3 is a relative minimum. F changes from increasing to decreasing at x equals 3 pi over 4. So that means 3 pi over 4, comma, and you plug that into the original, and you'll come up with 3 pi over 2 minus 5. That is a relative max. Okay. Now, I'm out of room, so I'm not going to finish my sentences for my second derivative. Just note that your concave up from 0 to pi over 2, your concave down from pi over 2 to pi. You do have a point of inflection because you do have a concavity change at pi over 2, comma, pi minus 4. Okay, so we have some points that we can graph. We've got a max, we've got a min, and we've got a point of inflection. So once again, I apologize, I did not finish my sentences. I'm kind of running out of room here, and I know you wanted to see the picture. I have my graph going to pi. 1, 2. I've got pi over 4 as a special point, pi over 2 as a special point, and then 3 pi over 4 as a special point. When I graph these, I am going to estimate these. Now, pi over 2 minus 3 is going to be a negative 1.4-ish, so I'm going to put that there. Now, if you have a calculator, you can take these out exactly. My pi over 2 is approximately negative 0.8, so I'm going to put my dot there. That's where I change concavity. 3 pi over 4 is approximately, it should be just a little bit higher. So when I do this, I've got that asymptote there at 0. There's my min. I've got my concavity change, and I've got my max right there. Okay, so I know that looks kind of weird. So it should be kind of this shape. Okay. Okay. So this guy is my max. This guy's my min. This guy is where I change concavity. Okay. So if you can imagine that being just a little more curvy right here, but not hitting the x-axis. Okay. Okay. So you're finding the first derivative. That's letting you know about increasing, decreasing, relative extrema. Those relative extrema, we want those in point form so that we can plot those. Your second derivative is telling you concavity and points of inflection. Your point of inflection, you also want that in point form so that you'll be able to graph those points as well. When you're graphing, make sure you are showing that concavity change. All right, that's it for the examples for you. Thanks for watching.